I'm Leanne Sherry, and I'm working with Jason Stallmaker on a project to discover stuff about the fine structure and isostructures of lithium. Lithium is interesting because it's a simple atom and only has 3 electrons. That means that theorists can do a lot of calculations at high precisions with it. And there are 2 stable isotopes, so we can study isotope shifts. And the D1 and D2 lines, which are what we're studying, are at 670 nanometers, which is a really easy wavelength to make in the lab. And there's a lot of discrepancies in measurements that have been made in the fine structure splitting the isotope shifts. So we're trying to make an experiment to help resolve some of these discrepancies. Here's a simplified model of an atom. And it's getting excited from an S state to a P state. And the fine structure is a little bit more complicated than that, when it arises from relative state corrections and quantum electrodynamic effects, and the spin-orbit coupling. There's the spin, there's the orbit. The spin can be either spin up or spin down. So we get 2 different states because of that. So we're studying the D1 line and the D2 line in the lab. And there's a lot of discrepancies in the fine structure. You can see there's 2 different graphs from 2 different isotopes. And you can see all the variations in the splitting, the measurements. And the red lines are the calculations. And they're pretty far off from the experimental results as well. And we're also studying the isotope shifts. There are 2 stable isotopes, lithium-6 and lithium-7. And the isotope shifts are caused by the mass effect and the volume effect. The mass effect is the difference in mass between the 2 isotopes. And the volume effect is the distribution of charge in the nucleus. It changes with the 2 isotopes, so that changes where the energy levels are. So we can learn valuable information about the nucleus from this. So we can learn about the charge radius of the nucleus if you compare the experimental results with the theoretical calculations. And the isotope shifts are pretty large. They're 10 gigahertz, which is a really hard to calibrate frequency in the lab. So we're working on an experiment to fix this. So to do this, we're using an optical frequency cone, which we'll talk about in a second. So, and these are the graphs of the isotope shifts that people have measured. You can see there's also a lot of discrepancies in that. So an optical frequency cone is a special laser that's made up of lots of ultra-short pulses that are separated by a radio frequency called FRAM. And in each one of these pulses, there's hundreds of thousands of different frequencies. So, and this entire cone structure is offset from the origin by another radio frequency called F0. We can look at both of those frequencies in the lab, which means that we can relate them with an equation to figure out the frequency of any mode in the structure. And a mode is one of these ticks here. And so with this equation, we can interfere to light with this and figure out what frequency it's at with this equation. So how the cone was made with addition of modes. Those are all the different frequencies. So as more and more of them interfere, you get shorter and shorter pulses. Looks like that. And we try to mode lock the laser, which means that the pulses only go in one direction from the cavity. Here's our cavity right here. There's here, there, and there, and there. And this is where the pump beam comes in. So it comes in and goes through the mirror and through the crystal, and it makes the bow tie sort of shape. And it comes out right here. And here's a picture of what the light looks like when it comes out. So you can see all of the different frequencies. It's the rainbow. Our final experimental setup will be that we will cool and trap lithium atoms with lasers. Then we'll probe them with an extended cavity diode laser. And then we'll interfere the diode laser light with the cone, figure out exactly what frequency it is. And then we'll look at the fluorescence of the excited atoms from the lasers, and then be able to compare that and figure out the frequencies of the transitions in the D1 and D2 lines. So our current status is that we've stabilized the cone reference to an atomic clock and GPS. So right now we have an absolute accuracy of the cone with 10 to the minus 12. And we've built the extended cavity diode laser. And we've made a laser cooling program, so we can see what happens when we cool the atoms. We made progress from the design of the vacuum system for the cooling of traffic. That part right there. And once we get the entire experiment set up, we hope to get 5 kilohertz accuracy, which is a factor of 200 better than the current discrepancies in the measurements. Any questions?
So you're saying you're going to get really small error bars. Is that what you're saying?
Yeah.
Of course, you don't know where you're going to end up on the graph.
These are just a plot of the weighted mean and the difference between them. So our this is 500 kilohertz right there, so will be 100 to that. So our spot size will be smaller than those.
Right.
What other possible systems could you study after you've targeted lithium-6 and 7? Do you have to look beyond that at all yet?
We can do any of the alkali atoms. We hope to do sodium.